Hello, and thank you for listening to the October call of the Nuclear Fusion Shark Tank. We have a number of interesting things on our agenda this evening. We have two great companies. The first, Horne Technologies. Horne Technologies was founded in 2008 in Denver, Colorado, with the purpose of developing a superconducting Biconic cusp, very similar to Lockheed-Martin's approach. The company was an early adopter of superconductors and in 2017 demonstrated 10 minutes of plasma generation and control using Biconic cusps. The firm is looking for private investment to augment VC funding taken in the summer of 2019. The other company is Compact Fusion Systems, which appeared in the August call of the Nuclear Fusion Shark Tank. CFS was founded in 2017 by Dr. Peter Turchi, Dr. Simon Woodruff, and Dr. Ronald Miller. The company is seeking $4.5 million in private investment to augment $4.5 million in government funding to develop a liquid metal compression of a field reverse configuration. Additionally, we're going to be discussing the U.S. Navy fusion patent, recently filed by a Pax River employee. Spoiler alert, this patent has very little physical basis. We're also going to be premiering a brand new database developed by Mr. Sam Wurtzel. This is a Wikipedia licensed database containing fusion metrics over the last 60 years and geared towards investors trying to understand progress in this space and critical investments that need to be made. Hope you enjoy the call. Tonight is Mr. Tanner Horne. I met Tanner 2 years ago in Denver, Colorado. I have to mute something. And Tanner is a classically trained vacuum specialist. He founded Horne Technologies in 2008. With the premise of applying superconductors to a Biconic cusp system. So the premise was very similar to what Lockheed is doing, where you inject plasma into the center and the plasma's diamagnetism would reject the outside field, leading to an enhancement on the trap. So Biconic cusps had been studied previously, probably before 1980 extensively, but were abandoned because of obvious problems with cusp systems. But when you apply superconductors, it's almost like a whole new machine, really. So Tanner, in 2017, was able to demonstrate 10 minutes of continuous plasma generation and control, which is a milestone in extreme vacuum. And now he's accepted some private capital from Free Radical Ventures in Denver, and he's looking for some more private capital to augment his work. With that, Tanner, are you ready?
I am ready. Can you hear me well?
Yes, go ahead and start your video.
Okay, thank you to everyone who's on the call. I really appreciate being here. We have a short presentation and a little video for you. This is pretty high level, so if you have more technical questions, I'd be happy to answer them later on or through email. So with that, we'll get started. Hello, my name is Tanner Horne. I am the owner and researcher at Horne Technologies, and we are developing a superconducting shielded IEC hybrid device. We are combining rapid prototyping to advance these devices for possible fusion energy. Horne Technologies is a small company founded in 2008. We developed our first prototype in Montana in 2017, had our first plasma in 2017, and recently acquired some seed funding for future validation experiments. For more than half a century, we have been working to produce fusion as an energy source, and it is just not yet materialized. There's been many concepts that have tried everything from mirrors, tokamaks, laser-induced fusion, field reverse configurations. So what do we really need to do to try to break this mold and develop a viable fusion device that can someday produce energy? Well, in 1903, the Wright brothers developed the Wright Flyer, as you can see here. It worked the first time, it was great, and it was perfect. Now, that's clearly not what happened. And this is what we believe is some of the issue with fusion is there's a lot of interest in going right for something that's perfect and is going to be phenomenal the first try. It actually takes a lot of iterative manufacturing to develop new ideas. With fusion is the cost and complexity of these devices to really use that type of technology to advance the field. Additionally, one of the most major markets that fusion would be good for is in outer space. In Earth, there will always be the capability to use fossil fuels, and competing with them may not be economically effective. In space, you also have to have a piece of equipment that is not super heavy. If we want to develop power
our really only option in space is solar, and it just does not have the power density if we're going to go to planets like Mars. So certainly there is a huge market to be tapped in the space market with fusion. One of the biggest obstacles in space, of course, is weight. ITER is estimated to weigh over 23,000 tons. That is not something that's going to be easily loaded on a rocket and shot to Mars. So if we're looking forward in uses of fusion, the space market definitely needs a system that is lightweight and manageable for something like a launch vehicle. These restrictions and design criteria were used to help formulate the technique that we want to use for our device. The technique itself must lend itself to rapid manufacturing because that is really where we believe that the gain is going to come from. Low-cost iterations are important in making that happen, along with minimum complexity. Ideally, the device also must be lightweight for future space use and possibly have the use of advanced fuels. One of the first and most simple designs for fusion devices is inertial electrostatic confinement devices, or Farnsworth Fuser. These have been around for a very long time. They are very simple to construct, but they have not been useful for energy production. There are too many loss mechanisms associated with the design. With this design in tab 1, you can see that the fuel is accelerated towards the center electrostatically. It passes through a grid which is negatively charged, that ions are attracted to, and some few of the ions collide to make fusion. This is a great heating method. It is simple to construct. You can reach fusion temperatures with modest voltages, but too many of the fuel ions run into the grid. This has plagued these devices since conception, and then although research is ongoing, they have simply not proven to be useful for energy production. In an IEC, there are two of the most major loss mechanisms. Grid collisions are the first. They offer a major reduction in inefficiency as your fuel runs into the grid. The grids also heat up and act as cathodes, releasing electrons and wasting energy that is input into the system. Grids interacting with the plasma also overheat, causing a very lossy mechanism. Also in an IEC, there are thermalization losses. The system is not fully thermalized in the plasma, so hot gas loses its energy to cooler gas. All cusp systems are non-thermal. Common misconceptions that we wanted to go over was the glow from these fusers, or star mode, is actually electron discharge. This is visible energy loss, and something that needs to be overcome in order to make these less lossy. In order to go after the loss mechanisms, we decided that the first thing needed to happen was to reduce grid collisions. Here, a superconducting magnetically shielded grid is used in place of a standard metal grid. Your fuel ions then, as they're attracted to the center of the device, are diverted around from the magnetic field and do not interact with the grid as much as they normally would in a standard IEC device. Since the strong magnetic field diverts ions, the grid is also cooler. It is cooled by liquid nitrogen, so it is very cold. This also reduces electron emission that you would have from a wire or other type of device. Using these superconducting magnets in opposing field also creates a very useful configuration. The opposing magnetic fields of strong curvature create what is called cusp confinement. What we have developed is a spindle cusp device. It's very simple and useful for our experiments. In the center, the plasma is momentarily contained in a null portion of the field. This is due to the plasma being diamagnetic and pushing out against the grid field. Temperature scales with pressure, and the higher beta you can achieve in your device, the more efficient it will be. For comparison, tokamaks generally are less than 0.05.
This cusp confinement aspect of the project is probably the most exciting to the people at the conference, and we hope that it has a large scientific value. When we do the testing, we'll be looking at multiple geometric configurations, and looking at things like the differences between point cusps and linear cusps. We're also going to explore the parameter space with temperature, pressure, and field strength, and a few other variables. All of this is enabled by the technological advantage of Rebco wire and the ability to use rapid manufacturing. Now, although the initial system was designed around IEC heating, this concept may not be the most ideal. It does have large potential differences, and it is a non-thermal situation. Both of these are aspects of IEC heating in the past that have been undesirable. This system is very versatile in that we can accept many heating schemes. Other schemes include things like neutral beam heating, which has less potential differences. And the system is also being set up so that we can operate in pulsed mode. This is going to allow us the exploration of pulsed IEC heating, which we believe is worth exploring.
So the enabling technology that we are going for is really a hybrid method based on what was previously a very lossy mechanism. In order to achieve the most efficient device, we're combining 4 or more technologies and manufacturing concepts to be used in the design. The first is inertial electrostatic heating. The second is a magnetically shielded superconducting grid. The third is the possibility for high beta cusp core operation, and a proprietary ion thermalization loss mitigation method. This all, additionally, is enabled by continuous operation. This is a huge advantage over a lot of other devices that have been produced because we can operate for as long as we need to. Using this low-cost method with new technology and new materials, the most major advantage is the ability to use rapid manufacturing. The materials are available commercially and affordably, and rapid manufacturing can be applied to fusion for the first time. This is a game-changing capability which has not been accessible in the past. High-temperature superconductors are the enabling material that also makes this technology possible. Many different concepts for fusion energy are currently exploring high-temperature superconductors, but we have already implemented them. They are cooled with liquid nitrogen. They can handle currents that are much larger than copper wire could ever offer. They handle high field, and they conduct with no resistance. This increases the efficiency of the device, although they are very expensive. At $50 to $70 to $80 a meter, this wire comes at a cost. Along with the other devices that are pursuing fusion and concepts, we are looking at the standard typical reactions. Deuterium-deuterium is our first candidate reaction, as it is most readily available. It is easy to do, and it doesn't require tritium, which is much more rare and hard to work with. In order to gain more energy, tritium could be used in such a device with a greater than 100 times energy gain, but that of course is for versions down the road. And further down the road, looking ahead to space travel, this device also has the capability of potentially being used in the future with aneutronic fuels or advanced fuels. These are significantly more difficult and likely not to be used for a very long time, but is highly desirable for the space market, and a device that can burn advanced fuels would certainly be desirable. So Horne Technologies has taken all of this technology and applied it to a superconducting cusp research device. We demonstrated our first operation in 2017 and have developed the first superconducting spindle cusp. This is the first application of Rebco superconductors in a cusp confinement device, and we've demonstrated the vacuum and cryogenic technology to make that possible. There are 2 coils in this device, each with half a Tesla of field capability. They can be operated independently or in synchronization. We demonstrated the full adoption of these superconductors in 2017. We had our first plasma, and we have been using this chamber since. Here's a video of the first device in operation. This is a superconducting spindle cusp device with the coil you can see on top and bottom, with a high pressure plasma currently in it, Normally the operating pressure would not be quite so high, but for visualization purposes, this is much more advantageous. The plasma, you can see, is controlled by the two coils. The coils can be operated independently, and currently in the video, they are being shown to be turning up and down in order to increase or decrease the field strength in either coil. This device was fully operational in 2017 and has helped drive the technology that we are currently pursuing. Horne Technologies is looking to gain some strong advantages with the technology we are pursuing by adapting the first operational high-temperature superconductor device. No other group has publicly demonstrated a full continuous operation cusp confinement device. Generally, they use conventional magnets, which limit to millisecond tests and rapid measurements. Large international projects like ITER will never service the space market due to their weight, and likely will not provide grid power for many decades. Previously, national funding has been allocated to large government research programs that have produced no break-even system over 50 years. This is kind of the mold that we would like to break in fusion by taking advantage of the rapid manufacturing capability that the new materials and technology provides. So where are we going from here? Our second generation device is currently under construction. This device is for validation and optimization of the technology. We are using a large 4-foot by 6-foot chamber with an improved coil design, improved cryogenic cooling, and we'll be going after 7 total experimental configurations over the next year. We are increasing the field strength, and the whole system is designed to handle up to 5 Tesla and be capable of that down the road. Our initial testing will probably operate more around 1 Tesla per coil. This is our validation of the technology, and we hope to gather data to get the recipe to yield the parameters for net energy. Horne Technologies has been a completely privately funded endeavor, and just this year, in July, we have acquired additional seed funding to accelerate and produce a second generation device. We're looking for funding to augment that seed funding to improve upon the capabilities of the device and accelerate the timeline as we go forward. Our path to fusion in 2020 involves a fully operational large-scale second-generation device in the first quarter. We will begin experimentation early next year. We're moving to a new facility in 2020 and hope that experiments conclude before the end of the year 2020. Horne Technologies has a 3-step business plan, with the first being developing proprietary technology to adopt this device and superconductors and develop a first-generation prototype. We have already completed that. The second is to develop a second-generation device demonstrating feasibility, scalability, and to optimize parameters for a possible net energy device, which would be the third device. This full-scale net energy capable device would be the one that we would eventually want to reach break even. As with all groups, striving to achieve scientific net energy is the goal. From there, we would position ourselves to be a power company or license the technology for power production. Horne Technologies is now proud to be a member of the Fusion Industry Association, promoting fusion technology and market development nationwide. There are many companies that are now banding together, and this is great collaboration for a common goal of generating fusion energy for use. The race to fusion is heating up, and it's an exciting time for everyone who's involved. I now will give you a quick virtual tour of our shop and first and second generation devices. After that, we'll break for some questions, and you can always send me an email if you have more. Welcome to the Horne Technologies shop. We're getting ready to transition to a new facility soon, but I thought I would give you a sneak peek of what's going on and what we've done here and kind of tell you where we're going. So behind me right now is our first generation superconducting device. This is one of the first superconducting devices of its kind in the world. We are using a spindle cusp configuration for our initial experiments. This device proves out the initial technology and the ability to adapt high temperature superconductors to this type of a plasma device. It is externally cooled with liquid nitrogen, and the high temperature superconductors are wrapped around on the inside of our two spindle cusp coils. With this device, we've actually managed to measure a slight increase in density of plasma in the null space of the spindle cusp and really proven out all the technology. This is a ultra high vacuum capable system, and it was actually operational in 2017. The entire device was built, designed, and engineered here, and we will be moving on to a much larger test version after this. It's been a really great device, and it's kind of a historical one now at this point. So we'll move on to our next generation. All right, and here is our new second generation device that's currently under construction. We hope to have it operational first part of next year at the new facility. This is where things are really going to start to get exciting. So what we're doing here is scaling up this cusp confinement concept with inertial electrostatic heating, and this entire chamber will hold multiple configurations of the cusp configuration, and will demonstrate all the feasibility and scalability of the concept. This whole device will run probably most of next year. We currently have acquired seed funding, which is supporting it, and it's going to be very exciting. We hope that the information gathered from this device is very conclusive and shows that we can use this at scale. The technology is very similar. We'll be using high temperature superconductors. This device will be capable of nearly 5 Tesla on each coil, which is pretty significant. The technology is really going to be proven out, and we hope to have some really good success with it.
Tanner, is that the end of the video?
No, it just locked up.
Okay. So 5 Tesla fields is what you're aiming for, right?
Well, the system is designed to handle that, but initially we'll probably start out around 1. It takes a lot more work to get to 5. But if we're going to design it to do, might as well go big or go home. Let me try to get away from the PowerPoint here. It is completely crashed. Is there any? While we're doing this, is there any other questions from anybody?
I have a question.
Yeah.
What kind of diagnostics are you going to put on that new machine? I noticed those need ports.
Well, and also, what kind of diagnostics did you have on the first machine? So we had limited diagnostics on the first machine. Sorry, I can hardly hear you guys here.
He asked what diagnostics were on the first machine and what diagnostics do you plan to put on the second machine?
So diagnostics on the first machine were pretty limited. And we are keeping that kind of close to our chest here, but the plasma parameters that we measured with that device, we certainly need to validate with much more by diagnostics in the bigger device. So that's really where the second generation is for. And the diagnostics, there's just something that we're kind of working on right now.
Okay. Okay. Any other questions?
Yeah.
Yeah.
You mentioned a couple ways that you plan on heating the eventual reactor, but how was the first generation machine heated?
So the first generation was purely a plasma physics device. We actually were not at high energy with that device. And it was electrostatic heating.
Okay. And you've got liquid nitrogen at your facility?
Yeah, yes.
Okay.
So as long as we have liquid nitrogen, we can continue to run.
Okay. Any other questions?
That was really a half Tesla in those small coils?
Yeah, a half Tesla is actually pretty easy to get to. As you start going up from there, it's exponentially harder. So they run comfortably at a half a Tesla.
Okay. Are there any questions from the community? You can message me. Anyone?
I'm curious who wound the coils, or if you wound them yourselves, and which manufacturer provided the tape.
Yeah, so there's a number of manufacturers. We don't want to go into the ones that we use, but they're American-based, and I designed and built the entire system myself. So yes, I did wind it and put it all together.
Questions from the crowd, from the audience?
Tanner, hi, it's Dan Prater. How are you?
I'm doing well. How about you?
How's your wife doing?
She's doing pretty well. We got the newborn upstairs, so.
Oh, fantastic. Okay, so I'm going to ask you about this thermalization thing, and I know you're not going to tell me what your secret sauce is, but I want to know where you're at in your IP.
So, well, we're just getting started, really. Just kind of keeping it quiet and just doing fun little experiments. So thermalization is a major issue with all of these style of devices. It's not limited to what exactly we're doing. So really, with the second generation device, we want to prove out that we have the capability to try to optimize so that effect is not dominant. And that may or may not be successful, but it's something we want to shake out of the second generation.
So we know that the plasma thermalizes, and then you got beam target situation, and we know that's not a very good place to be. We know that doesn't work. So are you worried about that? Are you concerned about that in any way?
No, I mean, I know the criticism of that, and I think it needs to be explored further. I certainly think that we need more experimental evidence to back up, pros and cons of those type of concepts. And with the we're going to do 7 different configurations in the chamber, and hoping that will really kind of shake out as something that's a complete game stopper, or maybe not.
Okay, so you might have a something that kills the effort, and that's a potential thing that could happen. And you think that you could uncover that in a period of time?
Yeah, exactly. So the experiments are going to be designed to optimize around that and prevent it as much as possible. So if the data is going to drive, really, is it going to be when we get done with the second generation device, we want to know 2 things. Is it feasible? And if it is, what is the scalability of it?
Okay. Are there any other questions?
Yeah. Tanner, this is Peter Davidian. First of all, awesome setup with doing the voiceover for the movie. I haven't seen that. That worked out really well.
Well, thank you.
Good. That right there was some innovation and fusion. Yeah. So, are you seeing any neutrons at this point?
So no, the first generation, since we were at low energy, we didn't really want to jump to conclusions immediately. So I did a lot of background work and developed the superconductor technology and worked with low energy plasmas. So with our second generation, we are certainly going to scale up to fusion temperatures, and we will see a lot of neutrons. That's going to be one of our major diagnostics, is just the counts.
Totally. Yeah, to just get an eye on. What count, or what total luminosity? How many neutrons per second total are you expecting out of your second generation?
I don't really even have an answer yet. So we'll find out.
Are you tempted? Oh, sorry if I'm.
No.
One last question?
Yeah, one last question, and then we got to move on.
Okay. Are you tempted by any simulations?
Well, I think simulations are great, and there's been a lot of that. But I first off, we don't have the capability here locally to do that, so we would have to partner with somebody. And secondly, I would really want to be able to feed data into the simulation so that we can, make sure everything is matching up and really know that we have a good simulation. So it's something we definitely want to look into.
Okay.
Cool.
Okay, all right. It's 9:30, so we have to move on to our next presenter. And so I'm gonna bring him up. Simon, can you hear us?
Yeah, I can hear you.
Okay. And I'm going to go take over this share here. So, Doctor, this next company is formed in Santa Fe. Let me just stop the video. Can you see that? No, I can't. Hold on. Can everyone see my screen?
Yeah, final, seek, and chart.
Yeah. Okay, good. All right. Can you see this video?
No.
Oh, yeah.
No. Okay.
I just see the Windows folder with all the stuff in it. Wire 1, wire 2.
Sorry, 1 second. Sorry, guys.
Hi, Ray. How are you doing?
Very fine.
Very good.
Good to see you.
Let me open it with a different player. So this next company was formed in Santa Fe, New Mexico in 2017. The team is first up Dr. Simon Woodruff, who has a long history in fusion. Can you see this? Can we see this?
I still see the wire 1, wire 2, wire 3. Just the folder with stuff.
All right,
I don't see any video.
Okay, share. How about now?
There we go. Yeah,
Aha.
compact fusion systems.
Okay, is it playing? Is it playing?
Yes.
Okay, good. All right, anyway. So Dr. Simon Woodruff received his PhD from the University of Manchester and then did a postdoc at Paul Bellin's laboratory and also at the University of Washington before founding Woodruff Scientific in 2005. As I said earlier, Woodruff Scientific is a rare example of a company that can make a living doing fusion contracts. So he ran that company from 2005 to present. He also founded SciVista, which is a data visualization company, which came out of this fusion work. And in 2017, he paired up with Dr. Peter Turchi and Dr. Ronald Miller. Peter Turchi was Princeton PhD and also did work on Linus. So he did fundamental research at the NRL on liquid metal compression.
You want a conference call?
And so he joined Dr. Woodruff and Ronald Miller to found this company. And so he's going to be doing, we're going to present a video that they generated. Simon, did I do a good job introducing you?
Yeah, that works.
Okay, do you want to say anything?
So,
Go on.
well, I'll just give a quick status update because I'm going to be called away to do stories for my 2 boys in a moment. But we're still waiting for this ARPA-E grant to be switched on. So we are still, I think the video was from August, wasn't it? So the story hasn't changed from August particularly. We're still in sort of holding pattern for this ARPA-E grant to be switched on. But once that gets switched on, then we can get all this equipment out of Air Force and start our design work for this double-ended FRC system and crack on with the hardware part of the problem. But yeah, that's the status. It hasn't changed much. But I will leave you with the video, and if you have any questions, feel free to email me. The email address is right at the end. It's simon@compactfusionsystems.com. But otherwise, we had fun putting this together, and I hope you enjoy it.
Okay, and with that, I'm going to start this video. I hope everyone can see it.
Hi, I'm Simon Woodruff. I am the CEO and a co-founder of Compact Fusion Systems. The other 2 co-founders are Peter Turchi and Ronald Miller, and together we're looking to develop a compact modular fusion power core for the utility market to put electrons on the grid. We founded Compact Fusion Systems in 2017 here in Santa Fe with the explicit intention of taking the stabilized liner compressor, a concept that was supported by ARPA-E at the time, through to commercialization. We've since found support from the New Mexico Economic Development Department, and that has allowed us to engage with scientists at Los Alamos and Sandia to help us design our new system, and we've found a seed behind our concept, the concept itself and how it works, and then I'd like to speak a little to the development plan that we have ahead of us for the next 2 to 3 years. The primary motivation for pursuing our concept is defined in terms of the economics. We're doing 2 things. First of all, we are designing to cost. Second of all, we have picked a compact system that has low capital cost requirements. When we design to cost, what we're doing is we're picking a target levelized cost of electricity that is cost competitive and using that as a constraint to define all of the target parameters that we need to achieve in our devices as we build them out and test them. When we're building more compact systems, what that means is that the total cost of the system will be much lower. The total capital cost requirement, both in terms of the development costs and the deployment costs will be much lower for our system.
Thanks to the ARPA-E initiative on controlled fusion, I came out of retirement about 5 years ago to revive the Linus program and its concept for a controlled fusion reactor based on stabilized liquid metal liner implosion on top of the plasma. The NRL program started about almost 50 years ago and was based on the Soviet program of about that same time, which actually derived from Andrei Sakharov even earlier as a notion for creating a hydrogen bomb. The Soviet program involved the implosion of thin aluminum shells or liners onto a trapped plasma. The NRL program started that way, and we were successful in obtaining very high magnetic fields, Gauss magnetic fields that way. Unfortunately, the calculations indicated that we would need energy equivalents of tens of pounds of high explosive if we were going to approach fusion conditions. And this was not the way to run a fusion program, since that would decimate the laboratory each shot. We went instead to liquid metal liners, which needed to be spun so that the inside surface would be stable against so-called Rayleigh-Taylor instability that would break up into droplets and poison the plasma. We did these experiments with liquid sodium potassium alloy, probably the hardest experiments I've ever had to do, and were successful at it. The outer surface, however, was not stable and needed to have a different technique of driving it. What I came up with was using annular free pistons driven by high pressure gas in continual contact with the liquid metal liner to be able to perform the implosion. And we built a system, a prototype we call the water model, that worked quite well in terms of developing the basic mechanics and showing repetitive implosion and re-expansion stably using this technique. We then went on to other systems, including ones that use sodium-potassium alloy, again, an adventurous opportunity, and developed that as well, and a larger machine.
Hey, Matt, the audio cut out for me. I'm assuming.
Initiative. So now we're starting off again. There are a lot of intricate details and challenging mechanical, electrical, and pneumatic engineering problems associated with this technique. Basic concept has probably been disclosed by patent 40 years ago. So it's all of the details of how to make it work correctly in the laboratory now that represent the IP that we'll be able to capitalize on.
So how does this system work? Well, we like to use the analogy of a diesel engine, where we have a cyclic compression of fuel to ignition. Our system, of course, is a little bit different in that the piston itself is a rotating hollow cylinder of liquid metal that collapses radially. And when it collapses radially, it forces the fuel to compress. We're not using a hydrocarbon fuel. We're using deuterium and tritium in a plasma state, which we inject into that hollow cylinder prior to the compression. Lastly, the energy recovery system is really quite different. When we burn the deuterium and tritium fuel, there's no drive stroke per se, as in burning a hydrocarbon fuel. Instead, there's a neutron that's released, and that's captured in that rotating liquid metal piston and heats that liquid up. And that's then pumped towards a heat exchanger, and then we boil water, make steam, and drive a steam turbine. So I'll take you through the compression sequence as we envisage it for our proof of principle device, the device we'd like to build out in the next 3 years. What you'll see is the plasma being injected from either end into a central region where the plasma collides, it merges, and then is compressed by the rotating liquid metal piston. The piston bounces and then expands back outwards, and the process then repeats. So where are we at, and where do we need to get to? Well, currently we're in the concept design phase for the compression system and the pre-engineering design stage for the plasma injection systems. And we've recently been awarded a small grant by ARPA-E to complete the engineering design of the plasma injection system, and also to relocate equipment from Air Force research labs. It's about $1 million worth of caps and switches and charging supplies, in order that we will be able to build out our engineering design. However, to complete the design of the compressor and to complete the build out of the fuel injection system, we will need further investment. So we are looking for support from ARPA-E to complete the engineering design of our double-ended plasma injection system, and also to complete the design of our compressor. We will be proposing a 3-year program where we perform bench tests of the compressor and plasma systems separately, and then integrate them into a combined test in year 3 as our proof of principle. This is the device that we will build in order to demonstrate that we understand the confinement scaling in the plasma, and understand how to build the next system that will be energy producing. So what will the proof of principle look like? Well, we have a conception. Here it is. It will be about 3 meters long. You can see all of the capacitor banks that are used to energize the theta pinch coils. Those are the coils that form the plasmas in the first place and inject the plasma into the compression chamber. You can see into the compression chamber there, and there's a pink glow currently, but that's where the plasma will collide and be compressed radially by the liquid metal compression system that we are currently designing. So the entire system will probably fit into our laboratory here in New Mexico. We may have to do some of the testing at an off-site location, but this is to give an idea of the scale. So the total cost of this activity will be about $9 million. We're splitting the program into 2 parts. First is the separate bench test of the compressor and the injector, and that we estimate to be about a $5 million activity. The integrated test will come subsequently. There's some machine upgrades that we need to do in order to perform the integrated test, and we estimate that to be about a $4 million activity. We'll be applying to ARPA-E when the next solicitation opens for this sort of activity, but we're also looking for equity investments that will allow us to reach our goals sooner and with greater focus. So thank you very much for watching our short video. It's been a lot of fun putting it together. If you'd like any further information, my email address is here. Don't hesitate to reach out. Thank you very much.
Okay, that's a great video. I don't know if even Simon's still on with us. Is Simon still there? Anybody?
I believe he left.
Okay. Well, we have another treat here, and it's just going to be a brief little presentation from Mr. Sam Wurtzel. Sam, do you want to talk?
Yeah, sure. So I mentioned earlier that I'm developing a database of fusion experiments that the intended audience are investors who are interested in investing in fusion startups. And I can bring it up on the web.
Yeah. Can everybody hear what Sam's saying online?
Yeah, I can hear him.
Okay. All right. Then so Sam, go ahead and type that in.
Yeah. So it's called fusionenergydb.com. And right now it's actually not public, but it's going to be public really soon once I fix a few bugs.
So just for those who don't know, Sam was in a graduate program at University of Colorado Boulder, working on what were you working on?
I was working on an emerging Spheromac machine.
Right.
I pressed something wrong and I lost it.
Oh,
sorry.
Okay. Well, want to try again? Yeah, let's try again. So he was working. What was it, 2005?
Yeah, this is at University of Colorado Boulder. University of Colorado built an FRC machine there. That anyway, yeah, it's a good story for another time. But energy database. So basically, the database is split up into a few. How do I use it? I see. Okay.
Yeah. Just finish out. Sam then left grad school, founded a company, and was an entrepreneur.
I founded a company, co-founded a company called OptoPart, which is a search engine for electronic parts that you may have used for buying op amps or capacitors or things like that.
Right.
And we sold the company in 2015 to an Australian company called Altium, which is for designing printed circuit boards. And I was there for about 3 years doing M&A activities, helping them buy other companies. And this database together, partially for myself, because I was trying to collect all the information on all the companies and all of the projects I heard about. It was just too much for me to keep track of. So I started keeping a spreadsheet, and then I started keeping a database, and then I made a bigger database, and then I said, hey, this is probably useful to the entire community. The key thing about the database is that the kind of information I'm storing are things that I think will be interesting to investors. I'm going to write some articles. These are actually not real articles yet. These are just placeholders. I'll have some commentary on these articles, but we have a link of organizations. And these are all the organizations these are private companies that work on fusion. Let's see if this works. Yeah. So these are private companies. These are the projects that they're working on. We have under researchers, this is both national labs and universities, all the projects that they're working on. And the idea is actually to have this cover all historical fusion history, starting around 1950. It's not complete yet, but yeah, we even have the Zeta machine from way back in the 50s. So in addition, I have investors and who they invested in, both public and private. So here we have RPE and all of the places they put money into, and a couple other links. But also want to show this project links, which is a view of all of the projects that I have in the database. And I don't have everything yet, but I will. And I have everything from the T3 tokamak from the 1960s to, I mean, there's a lot of stuff in here. So if we pick, say, the CMOD machine, we click that takes us actually to the MIT page. And so this is MIT, all of the machines at MIT, the CMOD machine, and then this is what I want to show is the data. Really what I wanted to do myself is to be able to make graphs of things like the fusion triple product over time and as a function of temperature. And so I started extracting things like density, temperatures, energy confinement times, and so on. And this is all available. It's going to be available through API. And if I have my laptop plugged in, I could show you some cool graphs I made that you've probably seen before, but you might not have been able to get to the data, or you might wonder, what paper is this actually come from? Because that's what I was wondering. And so I actually went back and I dug up all these papers. And these are going to be links to the actual paper. These links are broken right now, but you get the idea. So that's the fusion energy database. And any questions?
Any questions? Any questions from our online community?
This is a great effort. I just wanted to give an exclamation.
Yeah, it's really too bad you can't see the plots, because he can bring the data rawly in and then just use a Python script to generate plots, and he can enable anybody to do that.
Yeah. I'm gonna have some of the plots in the essays that I'm putting together. So when this launches, you'll see some of these plots.
Okay.
Great. Thank you.
All right. Last but not least, we're going to do a little bit of a view of this Navy patent. As soon as I can get. Okay. So as some of you may or may not know, about 2 weeks ago, a guy named Salvatore Pais, he actually has a PhD from Case Western University. He works at the U.S. Navy Pax River facility for NavAir. And he filed a patent on a fusion device. And so I'm going to take a look at it. This patent actually was picked up in a number of online publications and websites, Tech Explorer, Hack News, Popular Mechanics. So, you know, Dr. Stephen Dean has this saying. He says that usually when an idea comes out, you can usually find people that say, no, this is a bad idea, or you can find a bunch of people that will say, no, 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 let's take a look at it. So let's take a look at it. It arose from the NICE program, which is the Navy Innovation Program for Superconductors. And the thrust of that effort is a room temperature superconductor, which of course everybody is seeking. So that's where Mr. Salvatore works. It's not a classified patent, and that says a lot because there is a whole other classified patent system that he could have done this through. And if he's worked for the Navy, he is doing classified work. So that kind of says something right there, that they didn't go to a classified system. It's a complex, kind of a goofy reactor, and that typically is bad in my book. You usually want your system to be as simple as possible. The more complicated you make your fusion approach, the more opportunity for things to go wrong. So that's not good. The premise of the idea is to have these tubes that are superconductors, and then he's going to vibrate and move the tubes. And in his patent, he's going to make this claim that by doing that, he's going to increase the output of the superconductor. And I don't think that has any basis at all in reality. But we're going to look at it.
I would actually argue against that interpretation. When I read through it, his paper, it sounded to me not like it would increase the magnetic field of the superconductor, but it sounded to me as though he was suggesting that this would produce crazy high flux of RF energy out of the superconductor, which is equally false.
Okay. Okay. Yes. So the claims go from bad to horrible. And then finally, he's going to hold his whole chamber and tube at a higher voltage, which is a very difficult thing to do. So let's just look at this claim right up front. I actually dug up the claim, and it comes from this paper reference at the bottom here, which was published in 2016. I don't know how this paper got published. Was it published by him?
Yeah, it says it right.
Well, he was the author, but it was in this International Journal of Space Science and Engineering, whatever journal that is. It's a 4-page paper. If you read it, it basically starts with the equation for the Poynting vector? Pointing vector, yes, Poynting vector.
I'd like to jump in here. He also gets it wrong because the Poynting vector has a cross product that takes into account the direction of the electric and magnetic fields. And in his situation, at least for the rotation, they would be in the same direction. And so the Poynting vector would be 0.
Right. Yeah, and he writes it out as a function of these 3 terms, and then he says that if he changes these 3 terms, vibration, rotation, and translation, he's therefore going to get a high field output. And he's claiming 1 e to the 24th watts per square meter. And just as a point of reference, Z Machine's power is 1 e to the 13th. So even if we're being conservative, it's a 9 order of magnitude jump with no data. So as superconductor experts know, go on.
I'd like to jump in here for a moment. Part of the reason why, one of the things he quotes in here is that there's a surface charge density that he's assuming of 50,000 coulombs per square meter, which sounds like a reasonable number if you don't know what a coulomb is, but in fact it's quite far away from anything that's possible to be.
Right, okay. And as we know, superconductivity is a delicate thing. It happens in a long crystalline structure metal, and you have to form Cooper pairs in a long string to basically get the effect to occur. So it's a function of the manufacturing, and it's a function of the temperature and its orientation relative to the field that it produces and the structure in which it's made. So if you think about a delicate system and then shake it, it doesn't look like it's going to work. But I went ahead and did a little analysis, and I put together this quick 3D model. Based on the patent, I just assume a certain size. So I say, okay, let's make it 1.2 meters cubed. And based on the picture, let's back out what the thing would look like. So this is what it would look like. And I'm going to play this video again so people can get a better view. It's a chamber, Faraday cage, with plasma coming in through tubes on the side. And then they enter a conical section, which is wrapped with a superconducting wire. And then the gas is supposed to travel into the center and then hit a high magnetic flux, which will cause compression. That's the premise. Okay. So just looking at the magnetic fields, you can do a really simple, quick a field analysis of what the fields would look like. And of course, I'm not really using any numbers here. I did do one. I assumed a certain current per cross section of the Repco wire, and I picked a really conservative number just to get some sense of what the field strength would look like if you're a particle traveling along the axis of the machine. But just to go over it, so you have light field, and then you enter the conical section, which is very dense, and then you travel out through the end, and then you have a cusp systems. You would have a cusp system if you had 6 fields that were interacting like that. In the center, you'd have a null point. So I said, let's say we fill this thing with Repco wire. Let's assume that the wire is 60% of the packing, right? So it's packed so that the cross section is 60% of the actual. So we got current flowing through 60% of the actual cross section. And we'll just apply a simple Biot-Savart law to model the magnetic field along the axis, and we get that plot with a null point in the center. Now, for this, I had to assume that it was north-facing on all sides. If it was north-south facing, then the fields would interact, and then I don't think the plasma would do anything interesting. So that's what I went ahead and did. So if that was the situation, then we'd see what the plasma was going to do. You're going to have the electrons corkscrewing one direction, the ions corkscrewing the opposite direction. The gyro radiuses are going to be different, but you're going to inject plasma. It's going to come in. It's going to hit a dense field. It's going to corkscrew much, much tighter. Then it's going to get through, assuming it could get through. There's a chance that it might not. It goes in. There's in the center, there's a null point, so it's going to be some straight motion or from some large orbital rotational motion, and then it's going to hit the corners. And there might be a mirror point there. There might not be a mirror point there. To get a mirror, it'd have to hit these basic conditions plus some other conditions. And of course, mirrors, to get a perfect mirror, it's a tuning problem. Like high field might not work, low field might not work. You got to optimize this system. But this is a basic analysis on single particle motion. But I think the biggest, other than the outlandish, crazy claim about the superconducting conductivity, I think the other big problem with this approach is the idea that he's going to charge up the whole system and keep it charged while he's got a plasma in the center. So as you know, you're going to apply a voltage to sort of raise the potential of a metal, and you're going to have that voltage fed in from somewhere else. And then the metal's all everywhere, and you got plasma that's going to touch the metal surfaces. And if it's positive, it's going to draw electrons, and then they're going to draw ions, and we're going to have this sort of evaporation of the plasma. And so then what you're doing is you're pitting the plasma against your voltage maintainer, or the thing that's maintaining the high potential on the cage. And so the two are going to work against you, and you're going to take a ton of energy out of the system just to maintain the voltage. So if I was to give it number 2 problem, I'd say this charge is probably the second thing, aside from the 9 orders of magnitude jump. Any opinions from everybody else? Any thoughts? Any questions?
I've actually got another comment.
Yeah.
I think that this is an interesting case study in reading into it what we want to read into it.
Okay.
Because when I read through it, I read with my plasma physicist goggles on, like I'm sure you did, and I saw all of these different pieces that if I tried to force them into a plasma physics framework, they sort of made sense. But then when I read through it again with much more literal eyes on, I saw all the parts where he was talking about vacuum polarization and faster than light travel.
Yeah.
And that's where I decided that maybe it should be viewed more holistically. That's my advice.
Fair enough. Any other comments? Okay. All right. So we are about an hour. Is there any comments from the folks online? I'm going to unmute everybody.
I have a quick comment.
Yeah.
Reference in the patent to the similarity of the conical structure to an ion thruster. So it sounds like you could look at it as kind of like a spindle cusp, or like just a bunch of ion thrusters facing each other. And I'm not quite sure what to do with that. I certainly did not read into the faster than light travel or any of the other outlandish physics claims. So
Okay. Any other comments from anybody else? So I would call this this patent junk, and I would say that's what I would say. Okay. And now we are at 1 hour, and we're gonna call that the end of the Shark Tank. I'm gonna stop recording. Thank you everyone for attending. I know this is a big ask, and I really appreciate you taking the time. We may do another one before Christmas, but otherwise, hope everyone's doing well out there.
Thanks, Matt.
Yeah, cool. Thanks, Matt.
Thanks, Matt.
Okay.
Thank you very much, Matt.
Appreciate it.
thank you.
Thank you.
Thank you.
All right. Bye, guys.
Thanks, Matt. See ya.
Thanks, Matt. This is Jim. Bye.
All right.
Matt, you put so much work into that analysis. Wow.
That wasn't that much work. It was a lot of drawing.
Yeah.
Was that actually were those really the
No, they were just art.
they just are?
They're just art.
You have a very good hand.
Yeah.
Thank you. Thank you. For those who don't know, that actually after the Shark Tank is over, we turn off the recording. It's open time, and literally I just walk away, and I just let whoever talk to anybody if they want to talk to them. Because for a lot of people that are on this call, they're all over the country, and so this is an opportunity for them to connect in a more organic way, right? Peter, are you okay?
Yeah, I'm great. I just realized how dark it is in my room.
Okay, all right.
Light over a bit.
Peter, you want to tell people who you are, what you do?
I'm no one special. I work at General Fusion. Essentially, bad posture. I help the lead physicist with MHD simulations. That's pretty much it. I've been at General Fusion for 4 years. I have a master's degree in nuclear engineering. That's pretty much it.
Did General Fusion send anyone to APS this year?
Yeah, I think we are. I'm not going. We usually send someone to all the big conferences. So I assume there's at least someone's going.
Okay. I haven't seen anyone.
Yeah. You guys are usually easy to find with the bright red posters.
Yeah, we've been focusing a lot. There's actually people out in the woods right now. They're like sleeping out in the woods for our big compression experiment. So we've been focusing on that quite a bit.
Okay.
Yeah, it's cold. It's Canada. They're dedicated.
Oh, hi. This is Jim Boyden. Is my audio working? My video is not.
Yeah, Jim, we can hear you. Jim, you want to introduce yourself? Jim.
Yeah, I heard the question. I'm just trying to decide. Anyway, I have a PhD in physics, and I have a background in my fusion background as I was the person that introduced trial for energy to Paul Allen. I worked for Paul for 8 years, and then I have continued with Paul's company with a contract to monitor what's going on at trial for primarily. And of course, unfortunately, Paul died a year ago, so very sad. And anyway, so I continue to monitor the fusion industry for the benefit of Vulcan, Paul's investment company. And so I was wondering if anybody, there's this recent announcement a couple of weeks ago from ARPA-E about the funding opportunity announcement. And I'm wondering if anybody has any idea what the magnitude of the dollars that are going to be coming out of this FOA.
Yeah, it's $40 million.
I'm sorry?
No. For the ARPA-E beta program? Oh, was that high? I keep hearing. Oh, there's no, I thought you just got to hear the number.
There's no hits on the verge as an option.
No, well, and then that's not even an FOA that he put out. He put out a warning that I'm about to put out an FOA.
Jim, the number that was thrown around here was 40 million, but now we are debating it.
Yeah. Or did you say that here? 40 million?
I heard 40, but don't pull me on that.
Well, this was when I talked this about a couple months ago about
He's wandering around. We'll
Yeah.
Does Matt know how to contact you?
How much was the Alpha program?
The Alpha program is 30.
30.
I think it was 30 because I remember it was the same as the Alpha.
9 awards, roughly 3 million.
So I think the number is 30. Yeah, that's what I heard.
We can find Scott and get the lowdown. He's in Florida.
Okay, all right. Okay, I think that's the end of my questions. Anyway, that was a great job, Matthew, on digging into that strange-looking device. So.
Yeah. Okay. Well, get the word out because people,
All right.
you know, took it seriously. There needs to be, yeah. This forum can be a way to root.
Seriously, because I thought it was pretty obvious. It was just a crackpot.
It was put out though on, and take a look at the list of places that it showed up on.
Yeah.
I was getting it at work from quite a few places.
Me too.
Yeah, I got emails about it.
Yeah, I was getting emails, I was getting business managers, there's a new device, should we build this? And I'm going, no.
Yeah.
I think part of it is a false sense of credibility because of the Navy.
Yeah, exactly.
Yeah.
Yeah, exactly.
Yeah.
Yeah.
Oh, I see.
So even though we know it's not going to work, general public a lot of times doesn't know it's going to work, but it's general public that you have to convince that it's not going to work, and they're going, oh, it's cold fusion again. And that's a comment I get every once in a while.
Well, that wasn't cold fusion.
I know that's not cold fusion,
Like
but
power is cold fusion.
right.
Call that vacuum.
Exactly.
And we need vacuum polarization, but we already have problems.
It was very strange. There was stuff in there that we don't have a word for also. Things like removing the relativistic gamma factor via some means when you get to V equals half-2. There's not a word for that, but it's something.
Well, no, things that falls under the category of things that are obviously false. Given high points on John Moynihan's crackpot index.
Well, like, think about it. Oh, so I'm not familiar with that. I'd like to hear about that in a bit. But okay.
He's a mathematician. He invented the crackpot index.
Yeah.
It's sort of a checklist for things.
This is the one that's
I knew in
cites
my
yourself
area
6 points.
Right. And if you get a score of 10, then you're defined as a crackpot.
I think my experiment score is probably at least 1.
The second one in
No,
3 months.
the ideas that are different.
Really?
Ideas.
Yes. So companies actually got
Yes.
Because one of the things
you can't get up to 10.
Fuse has is multiple concepts where we just want to put electrons on the grid. Yeah. Independent of the kind of configuration. We'll focus on something. Obviously, we're always open to try new ones, so we're actively looking for those. And I've got a proposal from an officer in the Navy about 3 months ago that I had to go through and say, no, this is.
Anyway, so I'm going to say good night, guys. This is interesting today. I'll see you at the next one. Bye.
Okay,
Yeah,
thanks
nice
a lot,
to meet
Tim.
you.
We really appreciate it.
Bye.
You're in Fuse?
Yeah, I'm with Fuse. So I'm working up the Napier bill now.
I have one question regarding Fuse.
Yes.
Are you guys still working on the plasma centrifuge heat engine?
One of the problems we're having to find is people to actually come up on site and work. So like a lot of the people that push for that are tenure track professors. So it's very hard to get one of them to leave their day job to come to work. And we're trying to figure out different scenarios to bring up professors. Yeah, you cannot get a tenure. You know, they may go on sabbatical for a year, but that's what 6 to 8 years. And most of them don't want to come up on site. So we're trying to find different scenarios. Plus, if we take a look at the way the workforce is being developed now, how many students out there are working on an alternative concept? There's very, very few of them. I mean, that's one of the things. I think we have to take the China approach and do workforce development. Because that's the one thing about the ENN. That ENN is taking 3 years to train their plasma physicists, and they're spending, so they're going to drop $300 million.
So you were at ENN. Do you know their budget numbers? Do you know their staff?
$300 million a year is what
that a real number? That's not the real number.
What was it? Oh, no, it was $100 million a year.
Yeah, 300 million.
It was $100 million a year. Wasn't that what they were going
It was over time. We realized that the dollar spent in China is like $10 spent in the US.
Yeah.
Plus everything happens 10 times faster. And so we saw the ENN facility where they're building. It looks like probably this for the Tokamak and a few of our solutions. And one makes PFRC. They were with you guys off.
They're taking inspiration.
Down to the Princeton on the foot pedal, or
That would be antenna shape. You'll see it. It's
nice.
Yeah, just as we did with the Soviets. And so what they're building, I mean, what they built, you know, in the amount of time it probably took, like, you know, planning meetings to happen here. They have like buildings, like up and running, like built, and the amount of time that it takes to get, you know, something machine, you know, like that's going to happen before you eat breakfast. So the speed is, and so to underestimate them is big.
It's like what they did with the AP-1000. You take an American design reactor, we can't even get one built in the US for $10 billion. They built, what, 6 by now?
So yeah.
Not only that, but they actually took that approach and they modified it to make almost a small modular reactor based on the AP-1000 that they're now using for desalination, or that so they claim.
We built something that looked like FRXL. We were using the tool that Simon is inheriting, hopefully, from the airplane. We use our NTF thing.
Sorry, what is the AP-1000?
It's a fission reactor. Westinghouse design. Yeah.
So ENN, for those of you who don't know, is a gas company. It's still natural gas. They're one of the major natural gas companies in China. And this is all, the reason all this is happening is because every 5 years, China puts out a 5-year plan. The most recent 5-year plan came out in 2017 or 16. And fusion was called out in the 5-year plan as a national priority. And in the subcommittee's report, not only was fusion called out, but alternative concepts, magneto-inertial fusion, and advanced target exploration. And so when this is called out at the national level, basically all private industry, public industry, and students, basically everybody, you know, focuses on that. And so there's a whole, you know, plasma physics is now a sexy discipline in China, and it has a certain amount of cachet because it's called out in the 5-year plan. It's a long-term national plan, and so the amount of resources that are going in there, I have some numbers written down on the order of tens of millions of dollars per, you know, per institution over a few years. You have to, but because of the purchasing power parity, that's like $100 million. And oh yeah, it's going to happen 10 times faster. I think that they're also trying to recruit a lot of international scientists to come and teach, and so they're making very serious efforts. And it's worth definitely.
That happened to Francis Theo. Francis Theo was the head of Hyperjet in May, and then he was recruited to China. They pulled him over. He was a former DOE program manager.
When you interviewed Mike, did he tell you what happened with China?
No.
So Mike Campbell, the head of the LLE, back when we were having funding scares, he got a phone call from one of their facilities and said, "We'll cut the check. You guys just have to work with us." And that is a mind-boggling thing that you get a phone call to the director of an NNSA lab for that sort of stuff. That's how serious they're taking it. And he had a bunch of stuff up. I can't remember all the presentations about what we think is going on over there. ICF. They're rapidly looking to catch up to NIP and blow past NIP. They've taken every lesson that we've learned and they're implementing it.
Yeah, I think it's good to have competition, and I think that yeah, there's a lot of smart people trying to work on this. It's good to have competition.
So this is the new space race. You can't affect what they're doing. Just focus on what you're doing. That's my thoughts. That's my.
Well, I can fill in a little bit of details. They have an INSET Institute for Nuclear in Haifei, and their budget, the number I heard was 400 million, and I don't remember if it was pounds or dollars. I don't remember which one it was.
I mean, it might be RMB, and but I have some numbers written down on that.
Something like that.
It's not $400 million US dollars.
It's 400 million.
It might be 400 million RMB, and
that's the Institute's total budget, and it's operated under the Office of the Chinese Academy of Sciences. They're the umbrella organization, and then this is a special key lab, state key lab that's focused on fusion and fission. So they do, at that institute, they do the ITER work, but they also do thorium explorations, and then they have this system called HINIG, which is a high neutron source beam system And then they also do other things that I'm not sure about. Like I want to say something like an FRC or a mirror machine has been investigated. They organized the Alternatives conference that you guys went to.
Yeah, I was at the conference.
Yeah.
I saw that FRC machine.
They have an FRC machine for real?
Yeah, but
They do?
It's more the size of the phone. This is small phone. Yeah.
So
it's not that big.
Okay.
It's almost there training. But ENN is building a big facility. And this is just one. There are other facilities. I mean, there's a whole bunch of topographic work too that I didn't see, but I think it's really something. And the conference was actually great.
I know anecdotally that India also was interested in an IEC approach to a hybrid fission fusion reactor, and they approached an American company, but then I believe Modi killed it.
How did you hear that?
From the folks at Apollo Fusion in conversation.
Okay. All right, we're breaking up here, guys. I think people want to go home and go to bed. They're exhausted.
Why do you have this at 9 o'clock?
Because
there's probably
Pacific time. Yeah, we got to get the people. They can't be. They got to log in at 6 o'clock.
You West Coasters?
Yeah, it's West Coast.
Yeah, I'm about to have dinner.
Yeah.
I'm hungry.
It's almost the sun out where you were.
Yeah, no, we don't have sun up here.
Okay,
That's why we need fusion.
No problem.
Thank you, guys.
I'm gonna shut down the video chat. Okay.
Cool. Thanks so much, Matt.
All right, no problem.
Thanks so much.
All right, I'll send you an email when we have the thing up on YouTube. Okay.
Great.
All right.
Great.
Bye, guys.
See ya.